All right, welcome everyone. Today we'll have Nick, and he's never told me how to pronounce his name, but I think he'll explain that in his talk. He'll talk about astroseismology in TESS, and I think Kepler as well. We're looking at hybrid pulsators. So please take it away. But also, if you haven't signed the QR code, please do so, because otherwise everyone thinks that Rafa steals all the food. So, right, thanks, Nick.
Okay. Hi everyone, thank you for being here. My name is Nick. I'm going to talk to you about my first year PhD project, which we did at periodogram in Belgium. It was funded by the Kepler Foundation, by the Kepler Scholarship. I'm also part of the Stellar Evolution in Full Glory project, where the logo is in the corner, which means the letters don't actually end up in Sol, but they're all in there. It's like an astronomy acronym, so that's fun. And I'm going to talk to you about hybrid pulsators and how we find them with machine learning. Little spoiler, we have a little star, which is a pointer is not pointing. It's pulsating and rotating, which is a spoiler. I always get asked, how do you get from my actual name to Nick? That's why I put it in the slides now. So it is actually a shorter version of a translation of my real name from Ukrainian to any other language, but then because you don't have this sound in English and other European languages, I just don't torture people anymore. So
how do you pronounce it?
It's Mykyta, but the A is like here, and it's quite difficult for people who don't speak Slavic languages, so I just don't torture them.
Can you say it again? Sorry.
Mykyta, but you don't have to. I will structure this talk in 3 different parts. And the first one is machine learning for astroseismology, but I guess most people don't have a background in seismology, so I'm going to briefly introduce what it is. So you're all well aware what an HR diagram is. So it's a graph that represents a relation between temperature or color in this instance and luminosity of a star. But actually, stars change in brightness over time, and we do it for different reasons. This is a so-called variability tree prepared by the Gaia collaboration. And there are different ways why stars change in brightness. So people often say, twinkle, twinkle, little star, when they look at the sky. And actually what you're seeing there is just after the atmosphere moving. So you're not actually seeing the star twinkling. But stars do in fact twinkle. And this is what we call a pulsation. And I really wish the pointer was working. So we're going to focus on this part of the variability tree. So this is a star that is pulsating. And so when you try to marry those 2 ideas, the HRD and the fact that stars are pulsating, you're getting something like this. This is a pulsating HRD. So as you can see, you still have all of your stars, but actually they're now grouped in different ovals, and those parts are called instability strips. So stars on the instability strips will excite pulsations, and they will oscillate. And so when stars pulsate, they become more and less bright. And we can observe those changes in brightness with telescopes. So it is kind of similar to how when I'm talking to you right now, my vocal cords are vibrating. And depending on the medium that I'm breathing, so the air, depending on its chemical composition, its density, its temperature, we vibrate with different frequencies. And that's exactly what's happening to the star as well. So depending on the physics and the chemistry inside a star, the waves propagating in a star will behave differently. And this is what the field of astroseismology is studying. So astroseismology is a way to look inside a star by observing the changes of its brightness over time. It has been an established field for several decades, and it's growing very rapidly, mostly because of the quality and quantity of data that is available to astroseismologists for analysis. So let's look at the hypothetical star and put a hypothetical person inside a star to see what they will be able to hear. And so if we do this, well, they have too much pressure. Okay, let's put them in a pressure-resistant spacesuit and see what happens now. Still died, very, very hot in this. Now let's ask some fairies to sprinkle some fairy dust and then make this person unkillable to see what happens now. What they can hear. Well, nothing. It's outside of our hearing range, so it's complete silence. But actually, there is a technique in astronomy and data processing called data sonification, where you can take the time series and then kind of pretend how it would sound like in the hearing range of a person. And so if we do this in a hypothetical star, or actually in a very particular star in this case, you would hear something like this. That's weird.
Is it connected to sound, George?
That's a good question.
Is it connected to sound?
That is underwhelming. How do I check this?
You know how to make sure that it's.
Oh, the,
Maybe like this?
Yep.
Okay, let's try it again.
no.
So is it because it's connected to the owl or?
Which, I mean, yes, but,
I can try this from my laptop. I can disconnect and connect again.
just try playing it from your.
No, there is no sound.
Go to the sound menu again and pick your, yeah, your MacBook.
Oh, there it is. Okay. So here you can hear the star pulsing. As I can see, it's happening quite periodically. And so by listening to this music of the stars, you can actually tell what's going on inside. We will come back to this particular type of star. Oh, no. Okay, so what are the actually types of waves that are happening inside a star? There are two main ones. I'm gonna talk about both of them. There are actually more, but we are not gonna focus on the other ones. So the first one is a pressure mode, or a P mode for short. It is a radial or a non-radial perturbation. So radial means that a star is expanding and contracting uniformly. And then a non-radial means that the spherical symmetry of a star that is expanding and contracting is broken. So it's basically an acoustic wave propagating inside a star, and it reaches its highest amplitude in the outer stellar layers. And P modes have a low period and hence high frequencies as an inverse. You can see here an example of such a pulsation on a time series of a star. The other type of pulsation in a star is a G mode or a gravity mode. Those are only non-radial, so the spherical symmetry is always broken for a G mode. And those are basically gravity or buoyancy waves, and they reach their highest amplitude in the near core region of a star. And here again, you can see an example of such a pulsation. So if you imagine in the simplest case, non-rotating star, you can approximate, you can say that it is a sphere. And so when a wave will propagate inside the star, it will break the spherical, it will change the surface of a star. And so the wave that is propagating inside the star is characterized by three mode numbers, and those are spherical degree, which is how many nodal lines appear on the surface, the azimuthal order, which is how many of those lines go around the equator, and the radial order, which is basically how many nodes you have inside the star that are oscillating. It sounds very complex, but actually, if you imagine a balloon, which I did not bring because it was raining and I wanted to buy it, but I didn't dare to go to Target in this rain. So if you take a balloon and you squeeze it repeatedly with your hands from two poles, you will be exciting an L equals 2 M equals 0 oscillation. Why? Because where you're pressing with your palms, you will have a line on the surface which is not moving, and none of those lines will actually cross the equator. On the other hand, if your axis of a star is like this, and you're pressing it repeatedly with your palms from the sides, this will be an L equals 2 M equals 2. So this process is called mode identification, which is assigning those numbers to waves. And this is the holy grail of astroseismology. So what people in seismology want to do, they want to assign the mode numbers to individual modes inside a star, because this can tell you what is happening inside. I will come back. This will become a bit relevant closer to the end of the talk, so you can for now forget this if you want. So now I will once again show you the pulsating HRD, and we will zoom in on certain. Yeah.
Can I ask a quick, just out of curiosity, is there any parallel to the quantum mechanical, like orbital, like they use the same letters, and it's also the spherical, like sphere harmonic function.
I think they might have drawn inspiration from it.
Yeah, because the
Mm.
letters are also the same.
Yeah. Yeah, but then, for example, there is a community of white dwarf seismology, and they call one of those letters a different letter. So
Okay.
it's, yeah. I think there might be something, might be onto something, but actually I'm not sure. Yeah.
Or these are spherical harmonics.
Yeah, that's very
So it's the math behind it's probably the same.
Yeah.
Yeah, right, similar, yeah.
But then again, so some people use different
Yeah.
notations.
Okay, yeah, fun.
I think you might be onto something, but yeah, I'll check this. You also may be curious. So now we will zoom in on certain parts of the HRD, and now we're getting to the actual B-type hybrids part of my talk. So the AF. So first we will look at the AF spectral type, so intermediate mass stars. And here you have those two interesting types of stars. The first one is a gamma Doradus star. So those types of pulsating stars are named after the first star which was discovered to be of this class. So those are G-mode pulsators. They have periods of pulsations from 0.3 to about 5 cycles per day. And then very close to them is the delta Scuti pulsators, which are P-mode pulsators. Also intermediate mass stars, but they pulsate in P-modes. So up to 0.25 days, the periods. And then if you go a bit higher in the mass and the temperature to massive stars, here we have slowly pulsating B stars. It's like a more massive and hotter counterpart of gamma Doradus stars, so also G-mode pulsators, except hotter. And then again, a counterpart of delta Scuti, but now hotter, and beta Cepheids, which are P-mode pulsators.
So typically the amount of time that the stars spend on this pulsating phase is very short with respect to the life.
So this is main. So I'm talking about the main sequence. Actually, they will spend most of their life in there. But actually, stars can also pulsate in the pre-main sequence and also the post-main sequence as well. So those specific stars will spend most of their lifetime pulsating.
So you said the P modes are pressure modes. What are the G modes?
Can you come again?
What are the G modes?
Gravity. So it's a gravity or a buoyancy wave. An analogy you can think of, like if you take a surface of a lake and you smash it with your palm, you will have a wave propagating to the sides with water being displaced up and down, and this is kind of a gravity. This is the closest real world analogy you can have.
So is there a difference between P mode and G mode, where one's transverse waves and the other's like?
Yeah,
Is that the
exactly. Okay, so those stars have been observed from ground for decades, but actually astroseismology has benefited significantly from space-based observations for many reasons. The obvious ones are you can have continuous observations, you can have no atmospheric effects, no light pollution, no contamination from small satellites, and so on. And so astroseismology from space has really been booming since Kepler. Kepler has provided up to 4 years of continuous observations of 160 stars. And this has been really important for gravity mode seismology, because as those have long periods, they require also long baseline observations to be resolved properly. Also, you have Gaia. So Gaia does astrometry for billions of stars, photometry for millions of stars, and some spectroscopy. It was never actually designed. Actually, fun fact, none of those satellites, besides Plato, were actually designed for seismology, but we are very good at utilizing data from other purposes. So Gaia was never really designed for variability studies, but it was recently shown that it can, this very sparse sampling of data, recover dominant and sometimes even secondary variability of Kepler and TESS quite well. Then you have TESS, which does actually an all-sky survey, so it's observing a lot of stars. It's the most complete catalog to date, with hundreds of millions of observations. And now, next year, hopefully we'll have Plato, and this satellite will do seismology of exoplanet host stars. So finally, some seismology in the main mission. But also, what is more exciting for me, for example, 8% of its telemetry will be dedicated to a complementary science program, which is everything not related to exoplanet hosting stars, and lots of seismology, including my science, will go into this category. So astroseismology from space has really benefited the seismic studies a lot. And this study that I'm going to show you right now will be one example of that. So this all also resulted in petabytes of data. And back in the days, people could just like look at light curve, which is a time series of brightness over time, and just click through it, and it would have been fine. But right now, it's really not feasible anymore because you have so many observations that in human lifetime, it is not really possible to look into them. I will speak from experience. I had to look at like 30,000 light curves recently for another project, and it took me 3 weeks of like clicking. This is not really the best way to spend your time, right? So, and this is exactly why you want to have machine learning. And so, seismology has been increasingly relying on different machine learning techniques, and I'm going to briefly talk about them. So, the first paradigm of machine learning, which everyone is familiar with, is supervised learning, and it is based on existing astrophysical knowledge. So, what it means is that you have a teacher who is assigning labels to those stars. So, a person like me or someone more smart than me is looking at light curves, and then they are saying, okay, this star is a Scuti star, or this star is a gamma Doradus star. And then you can, with those labels, classify other stars. The problem with this is it is time consuming, right? So as I said, you have to look at those light curves, and this is a tedious and lengthy process. And also it is constrained by the bias you're putting into your architecture, right? So for example, here we have the confusion matrices, prediction versus actual labels. And as you can see, the number of those labels is quite limited, right? So you will never find anything new with a supervised classification. On the other hand, you can also have unsupervised learning, which is based on underlying structures in the data.
Sorry,
Yeah.
is that actually true? So if you have a supervised method, but you have an anomaly, something that is not in the training set. Are there ways in which you could tell, for example, by looking at the distribution of probabilities over classes for a particular, maybe it will not be able to decide between one or the other? In the sense that maybe it's possible to say, well, maybe this one could not be classified in any of these classes, and maybe.
That's true. We can also have like an other class as well. We will put everything else. It is true. We can also have supervised anomaly detection as well. So it's also true, but it would, okay, I guess impossible is to an absolute of a statement, but it would be more difficult to discover something different with this kind of setting, right? This is where you could use unsupervised learning. So you could cluster data based on the underlying structures that are hiding in it. Problem is, it is quite difficult to evaluate, right? So in those cases of unsupervised clustering, so here we have, for example, 2 plots from 2 of my colleagues. Here they have overplotted existing labels, which they have from elsewhere on top of their unsupervised clustering. And then you can kind of tell what's going on, right? But imagine you didn't have those overplotted labels, right? So you'll just have clusters, and you don't actually know what's going inside of them. So using unsupervised learning for variability studies is quite challenging because you really have to like then go into each cluster and then see what's happening inside. So if you summarize those 2 approaches, you have the supervised learning, which is quite time consuming, and depending on the task you're trying to solve, it can require such a complex representative labeled set that it becomes even more time consuming than normally. For example, which it would have been for my project, which I'm going to get soon, I promise. On unsupervised learning, it does not require labels, but evaluation is very challenging. And actual labels are sometimes used anyway. So if you were trying to look for rare objects, which one of those would you use, right? So as I already said, you can use some sort of anomaly detection, which can be supervised, unsupervised. You can have imbalanced learning if you are looking for something rare. But what if we try something else instead? And here is where we can introduce semi-supervised learning, which so far in astrophysics and astroseismology has not been used practically at all. There is one other study besides what we did that used semi-supervised learning. So we wanted to see if we can rectify this research gap and see if it actually works. And so I introduce you the case of looking for rare pulsators. This is the last time I showed this, I promise. You already tired of the HRD problem. So if you remember our gamma Doradus and the delta Scuti stars and then SPB and beta Cephei, you can see that the instability strips actually overlap here and here. This is where a star is a hybrid gamma Doradus Scuti pulsator and a hybrid SPB and beta Cephei pulsator. So why is this special? Because remember that the G modes probe near core regions and P modes probe outer envelope regions. So this makes a hybrid pulsator a perfect laboratory for stellar astrophysics because you can probe almost the entire stellar interior simultaneously. This is something that very few stars offer you to do. So they have before been found in Kepler, which is one of the telescopes I've shown you, the 4-year-long baseline observation, and then the continuous viewing zone of TESS. Because of how TESS is observing, there's a zone at the pole which is observed almost continuously, which is also great for GMO studies, for example. But then there have been no all sky studies to date. And this is because it is difficult to do, right? So without the machine learning part, it is practically impossible to do the all sky study of those hybrids because they're just not found, right? So to do an all sky study, the study that will encompass the entire parameter space, and to have those objects, but there are very few. So let's find some more. Actually, here I show you the light curve from the Fourier transform of such hybrid pulsator. So if you look at the purple part, which is the frequency space, you can see here you have your G modes, and here you have your P modes. So very rich pulsation spectra, which allow you to tell quite a lot about it. Yeah.
Can you just identify them by looking at the periodogram? Is there like, is it because it's particular frequencies or?
Yeah, so remember I told you that the G modes and P modes have specific periods, and even though the cutoff between them is somewhat arbitrary, for example, some people say that the transition from G modes to P modes happens in 3.6 cycles per day, some say at 4, some say at 5. This is also because the rotation can very much influence how the modes behave. So if you have a fast rotating star and then if the mode is also propagating in the same direction the star is rotating, it will be shifted to higher frequencies. So your G modes will shift where your P modes might have already should have begun, right? So it is difficult, yeah.
But you could have a P mode and G mode at the same frequency. It's just that the waves are in a different direction. Is that not how it works?
No, because they're separated by the fundamental mode, so they will not happen at the same frequency for the star. For some other stars, you have P and G mode coupling, but this is not for those stars. Those would be for red giants. No.
So it is, you can always put like some period cutoff.
Yeah, but it would be arbitrary because we don't actually.
You know,
So yeah, so you can do it for a specific star very precisely, and then for a population, not so much because well, every star is different, right? And so let's say, for the sake of the study, that 4 cycles per day, like around here, is where your G modes stop and your P modes begin. And so you can see you have quite a, no, not a lot, but some G modes and then quite a lot of P modes. So this is an AF type star. So this will be a gamma Doradus Scuti hybrid. And this is actually very common for those stars to have a very rich P mode pulsation spectra. So you will have normally a lot of modes. Not always, but often. So one of the ways to do semi-supervised learning is positive unlabeled learning, and here we come to the machine learning part finally, which is a very fancy variant of binary classification, which is the simplest classification setting in machine learning. So normally in binary classification, you have a number of data points, and then some of them are positive, some of them are negative, and you have both that are labeled. This is not the case for PU learning. For PU learning, only a small portion of the data is labeled, and everything that is labeled is positive. And then none of the negative data is ever labeled. So how you would reason about this is the labeled is always positive, and unlabeled can be either an unobserved positive or it is truly negative. An alternative way to reason about this, if you are more of a negative person, is the probability of including a negative instance in a labeled set is 0. Some examples of uses of PU learning in the other fields include, for example, personalized advertising. So let's say an advertiser is trying to propose you different links to click. And so you click on some of them, which are interesting to you. It doesn't necessarily mean that other links are not interesting to you, you just haven't clicked on them yet, right? Another example is, let's say, medical imaging. So you can have images of a certain body part, and then for some people, they will find a disease. It doesn't mean that all other people on the planet don't have this disease. It just means those people have not found this disease in themselves yet, right? So you can see a common theme here, right? So it means that this setting is used to look for something that was not found yet, just because we have not looked at those instances so far. So how do we actually do this? So the pipeline of machine learning study in the astroseismology actually is very similar to what you do in any other field. So you start with data collection, then you preprocess it, extract features, classify, and then evaluate. So let's look into each of those steps. The primary object of study in astroseismology and variability study is a light curve, which is a time series of a brightness of an object over time, right? So this is what you get from one of those space telescopes I have shown you. This is I think it's data from TESS. So here you have different examples of variable stars. So the top row are pulsating stars, which is actually what we want. So I think this would be a G-mode pulsator, and this is a P-mode pulsator or a hybrid. And those are also variable stars, but they're not pulsating. So this is a rotational variable. A rotational variable is a star which rotates, and as it does, it brings chemical spots in and out of view. And this is what you see. Like when a spot comes, the star becomes less bright. And this is an eclipsing binary, which is like a binary system which it orbits around the common center of mass. And as it does, if you look at it at a particular angle, it will sometimes obstruct part of light. And those are the eclipses. So here we have a primary eclipse and secondary eclipse. Also not variable, but not pulsating, but variable. And you can have combinations of those. So for example, you can have a pulsating star, which is also rotational variable, or you can have an eclipsing binary, which is also pulsating, and different combinations, which makes it quite complex. And so once you get this, we have to pre-process it because data comes with different systematics. So what we do is we remove outliers, which are several standard deviations of the mean. Then each telescope also tells you if a data point is bad or not. So maybe something happened to the instrument, and then it will flag this data point is bad. So we remove those. And also we subtract a Gaussian smooth time series to remove long-term systematic effects. So if, for example, here you can see the original time series in black, and then you can see like it has a very strong trend, which is like actually four peaks. So we did trend those, and then, for example, we are left with the green as the final time series, which we will use. A common way to do classification in astroseismology is to look at the frequency domain features, which is something I have shown you before, the periodogram, which we have for our hybrid. So what people do, people often extract dominant, secondary variability, their amplitudes, phases, some other features from periodograms. So we already said that hybrids pulsate in different modes, so P modes and G modes. So let's make an assumption that there are certain parts of the frequency space which are more important than others. And some studies already done that. So for example, here are two examples by my colleagues. So here, this was a manual classification, so no machine learning. So here, the astrophysicists, they look at the two regimes before and less and more than 5 cycles per day. Here is an example of a similar approach, but with 3 bins, so less than 1 cycle per day, from 1 to 5 and beyond 5. This was a machine learning classification to look for hybrid pulsators, among other things. So this study looked for hybrids. This study looked at also other variables as well, but hybrids were included. So as you can see, bins can either be overlapping or non-overlapping. They can also be different in sizes, same in sizes. So we thought, okay, let's try to take this a bit further. And so we came up with a smart binning algorithm to extract features from the frequency space. So what we did is we did a Fourier transform for all of our targets, which are labeled hybrids, which we have. And then we calculated the cumulative power distribution. So the cumulative power distribution basically means how much power is already behind the distribution or is still ahead of you. So for example, if you say that there is a 0.6 on the distribution, it means that 60% of the power from your peaks are already behind, and then 40% is still ahead. And then we just simply map this distribution onto a set of linearly spaced bins, which results in something like this. So this algorithm will make it so your bins are finer, where you have more power increase, and then sparser elsewhere. So this will prioritize more important parts of the frequency space.
And these bins are equal amount of power, or
increase in power.
equal increase?
Yeah. And we do it again and again for all of our labeled hybrids. And then we simply average the bins. So the idea behind this is that it will give you the average important parts of the frequency space which are needed to actually find targets of your interest. But of course, the downside of this, if you are suddenly interested in a new class afterwards, you will have to redo everything. So it it comes with pros and cons. And so once you do this, you're left with something like this, which is the average bin edges for all of our labeled hybrids. And from those, we extract very simple features, which are the photostatistical moments and the amplitude of the highest peak. As I told you, normally people actually extract the frequency, but then we don't do this. This is because bin edges already serve as proxies for frequency. So if you also extract the highest peak, it kind of makes it a bit redundant. And so I call this short and sweet because that's what you need when you have millions of stars like I do. So no fancy features, just statistical moments and the amplitude. And then those exact bins are also applied to all the stars. Remember how we had our graph with positive unlabeled learning? So actually we will apply the same bins to all stars in our sample to try to find hybrids. So how does it work? Here I repeat the way that PE learning is done. So we have a bunch of labeled hybrids, which came from people who did the selection manually, which took them many, many hours. And we had 480 of them, which is our labeled data. Then PE learning also requires unlabeled data, which is almost 30 million.
Yeah, so sorry, so basically your data set now is 5 or like 50 because you have it 10 times per bin.
Mm-hmm.
I mean, you're training on that, you're not using
Yes.
your curtain.
Yeah, exactly. There are plenty of architectures which also use features from the time domain as well. So for example, if I show you this again, so for example, finding eclipsing binaries is done in the time domain because we have skewness of the flux as the main feature to do this. So it depends on what you are trying to do. So
We're about combining time domain features.
that's a good question. Ideally in variability study, in an ideal world scenario where you have like unlimited computing power, you would use all of this as a feature, right? Because you want to have as much information as you want about the periodicity of the stuff. However, this is extremely impractical. So this study is actually kind of a take on a dimensional reduction approach, right? So you want to try how you can reduce this very rich pulsation spectra in a few numbers. I mean, it doesn't end up being few, it's like 5 by 15, but it's still a few, let's say. Yeah.
Just on that, has anyone tried also encoding these data?
Yes.
Just using yours.
Yeah. There are a lot of people actually doing this right now. So you can do this both for the time domain and the frequency domain as well. So people are looking into this quite actively.
How does it compare to the manual feature?
Okay, so I haven't tried it for hybrid detection specifically.
Yeah.
It does quite well. It depends on the specific use you want. So there are quite some papers. So actually, I recommend this review paper. It actually talks about it.
Oh yeah, I've read that. Yeah, I'm reading it.
Yeah.
I mean, that's it, I like when people still do things manually rather than passing.
Yeah,
it
and
into a
I just
transformer.
very motivated. Yeah.
What was I saying? Yeah, so it's a very active area of research. That's my interest, and actually is in feature engineering. I like thinking about features. I like them also being interpretable. So it is not within my interest to do autoencoders, but to each their own. You know, I think this is exciting. So, and so yeah, so we have our labeled data, which are hybrids, which have already been found. We have a lot of unlabeled data. As you can see, the orders of magnitude are huge, right? And then you want to learn a decision boundary between those. You want to say whether something is a hybrid or if it's not a hybrid. So how is it done exactly? So once again, we have our labeled data and you have your unlabeled data. And so what you do is you learn simple decision trees. Those are great because those are computationally very cheap. You can learn as many as you want. And so what you do is you take your entire labeled set, so all of our hybrids, and then you also bootstrap the unlabeled data. So you select randomly, and you pretend all of this is negative. So remember, the idea of PU learning was that in our unlabeled data, there are hybrids which have not been discovered. And here we are pretending everything here is negative. And normally here is where people have a question, well, don't you confuse your classifier by this? But actually, so hybrids are quite rare objects, and so it was very unlikely that you would, I mean, you will include some of those unfound hybrids in your bootstrap, but also because you do this many, many times over, your confusion of the classifier you're introducing kind of averages out at the end, and so you come out with the unbiased estimate. And so you do this again and again and again, and you can do this as many times as you want, again, because decision trees are so cheap to learn. And then each of those trees will output a prediction for each object that did not go into your bootstrap. So for example, as you can see, here we had selected in the bootstrap this yellow data point. So we did not predict on this, obviously, because that would be not very smart. And so you predict on everything else. And then you average the probability of each object being a hybrid or not. Actually, we secretly do this twice over. So we do this whole architecture for the features in the frequency space, and also secretly the same for period space. So periods as inverses of frequencies. And this is because actually, so you can get more information about G modes in periods and frequencies. So we try to make it a bit more tailored to both hybrids, which have dominant G mode variability and P mode variability. And then as we have those average probabilities for both frequency and period features, we then average them out. And then this final prediction is the final probability of an object being a hybrid pulsator. And so now the final step is evaluation of the pipeline, evaluation of semi-supervised learning, and yes.
So just going back to that architecture that you've got here, have you compared to the other methods of doing? I mean, this is interesting. I haven't actually heard of this. But have you considered like other semi-supervised learning methods where, because you should have a set of negative samples as well, right? Because you said they're quite common. So you must know an equal number of negative.
Yes.
Is that not true?
We have not compared with anything else.
Right, but if you were to just train a supervised classifier, just going.
Yeah, but then, okay. So in those 30 million unlabeled light curves, you have many, many different types of phenomena. And so if you want to do it supervised, you will have to have examples of all of those phenomena, right? So I showed you the confusion matrices, which was a limited number of variable classes, but this does not encompass everything you have in on the sky, right? So, and even if you want to have like the other class where you put everything else, you have to have examples of this other class, of those other objects in this class. So it's kind of like a vicious circle that to find rare objects with supervised learning, you have to have examples of those objects, but also other objects. It is just so time consuming, it just doesn't make sense.
Yeah.
Does it make sense?
No, it does. It's an interesting thing.
So what you can similarly do, you can, for example, would be interesting, very interesting to compare with like a 1+ classifier, right? So this directly incorporates unlabeled data. 1+ classifier does not. There you only have labeled data, you don't use unlabeled at all. This will be a very interesting comparison. We have not done this yet. Yeah.
Hopefully, how long does this take to run for
So the classification is super fast. Its trees are super quick, right? The feature extraction, so that depends if you also count Fourier transform or not, because Fourier transform is the most expensive part. So if you do all of this, like if you just compute the Fourier transform, it takes like, I don't know, a bit more than a week or something. But then extracting the features once we have the Fourier transform is very fast. It's maybe like a day. So, but this is always like this part, like just the frequency space, like forget the bins, is the most expensive in variability studies. So yeah, this is super quick. Trees are very efficient. So evaluation of positive unlabeled learning is extremely complex. And this is my opinion is why no one is using it, because it is very difficult to actually say if you're doing a good job or not. So there is no precision in PE learning and therefore no F-score for this specific implementation. There are other methods which do allow you to estimate precision and F-score, but not available for this specific architecture. Recall is also a proxy because actually you don't have all of your positive instances, right? So everything from now on is a bit of a, not speculation, but approximate. So what we do to estimate recall is we set aside part of it and see how many of those we can recover. And so actually it is doing quite well. So there are different, so we have different types of data from TESS. There is nominal mission and extended mission. Those have different samplings. And so actually, secretly, we did classification not twice, but 4 times, because we did separate for nominal, separate for extended, because the sampling affects the recovery of P modes, which are short term pulsations, and hence they benefit from finer cadence. That's why you have separate means for hybrids that were hidden in the test set. So it's for both of them above 90. So just high recall doesn't actually mean that your classifier is performing very well just by itself, but it kind of gives you hope that if it is good at recovering back hybrids you hidden from it, it will also find you new ones, right? And then the mean for the unlabeled set is about 7.5%. This actually also makes a lot of sense. It basically tells you that most stars receive such low probabilities that they're not hybrids. This is very logical because hybrids are rare objects. So again, this is all how do I say this? Not as precise as you would have it for supervised classification. So this is much more challenging to actually judge whether you're doing a good job or not. So what you can also do is you can predict on labels from other studies. So people have, of course, done variability classifications in other studies as well. And here we, for example, predict on 4 other classes. And so there are very few that receive very high probabilities. And by that, I mean above 80, actually only 3 targets. And all of those are P-mode pulsators. This actually also makes, from astrophysical perspective, a lot of sense. So if you remember our periodogram for a hybrid pulsator, you have your P modes like in the high frequencies, right? But then in the low frequencies, where you can also have G modes, you can also have, let's say, an instrumental systematic, which will appear as a high P, or you can have a rotational variability, as I showed you on the graph before. And if our features come from the cumulative power distribution, it means that there are many objects that have the opportunity to be confused with a P mode plus something else, with being confused with a hybrid. So it makes sense that this class receives, on average, the highest probabilities from non-hybrids, but also that there are objects that kind of have probabilities above 80%. Then what you can also do is look at feature importance. Actually, here I call it bin importance because remember, from each bin we had 5 different features, and we sum all of those features up for each bin to see which bins are more important. And actually, if you look at the teal distribution, which is distribution of dominant variability of hybrids in the labeled set, the density of the part after 4 cycles per day, if you sum all of this up, is higher than it would be before 4 cycles per day, which means our labeled set is dominated by hybrids with dominant P-mode variability. And this also translates into bin importance as well. As you can see, bins with which cover variability in the P-mode regime are there are more important bins there than it will be here as well. And here in the period space, it is also the same situation too. This tells you that you should expect that you will recover more P-mode dominated hybrids in the high probability regime as well, which is actually exactly what ends up happening anyway. So this kind of like a little sanity check, and also kind of a spoiler what to expect from your classification. So what you can also evaluate on is on the from the astrophysical perspective is you can look at the distribution of fundamental parameters of those stars. And if you plot the distributions of temperature, radius, and luminosity for labeled hybrids and the candidate hybrids we have found, you will actually find that the shapes of those distributions are very similar. And in fact, the statistical test suggests that they have all been drawn from the same distribution. So without having any prior information on those properties, the classifier is able to find very similar objects. So this is reassuring. So you can also, once again, look at the distribution of dominant frequency and its amplitude. As I said, we have more P-mode dominated hybrids, both in the labeled and the unlabeled set, which we have found. this comes from at least 3 different sources. So I already touched on one of them. So the labeled set bias, it's because you recover what you put in your training set. Because we have more hybrids with dominant P modes, we also recover the same. Also, TESS frequency resolution is not optimal to recover all G modes. So actually, part of our labels come from Kepler, because Kepler has a field of view, and then TESS also covers this field of view. So you have the same objects observed by both. But Kepler has 4-year long observations, and TESS observations are 27 days long. So this is not sufficient to recover all the G modes you had in Kepler, and hence this is why not all so not all G modes which you would have had if you had a Kepler observation are recovered by TESS. And also, as I said, low frequency systematics also affects recovery of G modes as well. And actually, so this distribution is already with objects with commonly known TESS systematics filtered out. So if a dominant variability fell where you would normally expect a TESS systematic, we just remove this object altogether, even if it means it would have been a G mode pulsator with a systematic, it's just not there anymore. And then what I find very interesting is actually we improve on the bias we had. So actually, if you look at the height of the bins for the unlabeled and the labeled data, actually the height of the bins, the purple, are higher in the G mode regime than they were for EEL, which is our labeled sets. So actually, not only did we not work from the bias we have introduced, we actually improved on it a bit, which is reassuring. And distributions of amplitudes are very typical for the F stars and look very similar. So I get to the final part, which is the astrophysical insight which you can get from those objects. So this is a HRD. This is a graph of effective temperature. There's, I don't know why F letter is here, versus luminosity. And then this is systematic from Gaia. This is not us, this is a Gaia problem. So just ignore that. So by having more AF hybrids than B hybrids, we actually have been able to find a large population of both AF and B-type hybrids. This is actually because the morphology of light curves and periodograms are very similar for those objects. So not exactly as I will show you in a minute or two, but those objects, if you just look at the time series or the frequency space, are very difficult to distinguish without having temperature or spectroscopic information. But also, if you remember all the way in the beginning, I showed you distinct instability strips, and instability strips for those objects were not together, so they were disjoint. But actually here, so here you would have an instability strip for AF stars, and here for B stars. But like, what is this in the middle? Is there something going on? So actually, a lot of the studies in the last years have been consistently finding stars in between those instability strips. And there are 2 hypotheses about them. First, it might be rotation. So if a B-type star is rotating and bringing chemical spots in and out of view, they will appear cooler, and this will shift those objects in the direction of AF stars. But another hypothesis is, what if the instability strips are actually not disjoint? What if there is actually a continuum of stars from AF type stars to B-type stars? And we don't know this yet, because those studies have made this hypothesis but have not looked into it. So as a follow-up study for this project, we are trying to see if those are actually B-type stars which are rotating by fitting a rotational signal to them. What you can also do is you can look at the relationship of a dominant G mode to a dominant B mode. And here you have 2 distinct groups. First group is long period gravity modes and short period pressure modes. And the second group is short period gravity modes and widespread of high frequency component. So those are linked to different L numbers, which I have shown you at the very beginning, but also they come with different systematics. For example, here you can see very clearly some straight lines. And those are misclassifications which came from variable stars with a harmonic behavior. So for example, some eclipsing binaries. Some of them are still pulsating, but some are not. So there will have to be some post-processing of the final set done. What you can also do, which is very insightful, is to look at the number of peaks which you have per unit frequency. And so what is very logical is that actually that you find more density in the low frequency regime than in the high density regime. This is because G modes often appear as like cones of frequencies clumped together, and then there's space in period space, but not on frequency, which is vice versa for peak modes. So this is actually a good sanity check to see if you're recovering stars which make sense. But what is perhaps more interesting is to look at the differences between AF and B-type stars. And here you find that AF-type hybrids are denser in the P-mode regime. And remember how I told you that AF stars actually have very rich pulsation spectra in the pressure mode regime, which is a bit less so for B-type hybrids, and vice versa for the low frequency. For low frequencies, there you have B-type hybrids which are denser. So it also makes a lot of sense, which is also again a good check. And now I guess the most exciting part, as I told you, the holy grail of astroseismology is identifying pulsation modes. And actually, this is very complex, but I will show you a very simple example how you can do some of that. So what you can do is you can stack your period of frequency spaces one after another. So each of those rows will be this periodogram I was showing you, but then compressed to be very, very tiny. And so if you stack this for hybrid candidates which have dominant G mode, so we're looking at stars where G mode is the highest peak, you will find this very pronounced ridge. And this is a dipole prograde mode. So this is an L equals 1, M equals 1 mode. So you can imagine again your balloon, which you're now just squeezing from one side, so you're not doing anything from this side, but you're just squeezing it here. This makes it dipole. What makes it prograde is the wave is traveling in the same direction as the star is rotating. And so this will be this mode. Then you would also have an L equals 2, M equals 2 mode here. And then you would also have, not very visible for you, but visible for me, a secret third type of modes, which is a Rossby mode. We're not going to talk about them. They're very interesting and they're relevant for stars which are rapidly rotating. And actually, when it comes to rotation, so I don't know what's happening with my label today. So if you assume, so this will be a dipole prograde mode in 9 out of 10 cases, and 1 out of 10 it will be not a dipole prograde mode. If you assume that it is, you will be able to compute the near co-rotation frequency, because as you remember, G modes, they probe near co-regions, so a G mode is able to give you information about what's going on there. So if you assume it's a dipole prograde mode, you can get this. And the distribution of near co-rotation frequency actually look very similar for labeled hybrids and the unlabeled candidates, except this part, very obvious. So we have some hybrids in our candidate list, which are slow rotators, which is, there are 2 explanations. One of them is, remember those contaminants we have, so those may be those stars actually. Second explanation is there might have been some physical process which has slowed those targets down. So that's also an interesting thing to investigate. And so with that, I come to my conclusion. So with PU learning, which is a very underutilized framework in stellar astrophysics, we are able to get over 50,000 new high probability candidates, which allow you to do basically a full parameter space study of those objects from the more astrophysical perspective. It was done with a smart binning approach, which basically is tailored to extract those specific types of stars, but you can also redo this for any other object that you want. And this was possible at a fraction of a manual process, which would not have been actually possible in human lifetime at all. So this can be seen as a sort of dimensionality reduction and precursor to a ensemble seismology project, which will make it possible to study those objects in more detail further. So thank you for listening.
Thanks, Nick. Probably got time for 1 or 2 questions. Here, go.
I have a question about the frequency. So you said you can distinguish the modes between, like, if it's above 3.6 per day or so, then below it's a G mode, and above it's a different mode. But stars have different sizes, right? So the modes kind of, if it's bigger, then it takes longer to travel to the star, so it should be at low frequency, or is it like,
Yes.
can one generalize it
Yeah.
that much?
That's a great question. So remember how I was showing you, or not showing you, we were listening to a sound of a star. So this was, for example, a delta Scuti star, right? So it was an intermediate mass star, right? So that's why it was doing what it was doing. Now imagine if you have a red giant star. It's a very big star. So then the sound that you would be hearing would be like not like this, but it would be like, so the wave will be traveling very, very slowly, right? Yeah, so exactly this is correct, but then I think your question is partially this and also partially linked to the excitation mechanism of modes, right? So modes come from different physical conditions that excite them, and that's where you have a P mode or a G mode, and then also depending on which region it's probing, because one can propagate in the radiative regions and one cannot. So like it depends on where it's propagating, what excites it, and also the size of a star.
I think that's the hour. Let's thank Nick again for his time.